Next, we are going to see the next rule on another example. And that example is exactly the fact that we took for granted in the previous example. So this formula. Now we want to prove that without using induction. And the proof uses a classical trick that is commonly ascribed to Gauss, who supposedly came up with it as a high school student or as a middle school student, I think even. Well, it is an old idea. I think it goes back to the ancient Greeks actually. So what do we do? And I'm giving one version. The notes have a slightly different one. Well, if you want to prove that something is something else over 2, it's reasonable to just multiply the something by 2. So we want to prove that 2 times the sum, that should be n times n plus 1. Why? 2 times something is the something plus itself. Let's design them as a square. And now let me turn the second sum around. I think it's easier if I add one more sum into it, just so that you see it, just so that it looks symmetric. And now I want to reverse the summation order. So instead of starting at 1 and ending at n, I will start at n and end at 1. And now, instead of summing this parenthesis plus this parenthesis, I will reorder them by first summing this and this vertically, then this and this, and so on, and then this and this, and this and this. This is actually this rule here. So 1 plus n is the first pair. The next pair is 2 and n minus 1, and so on. The second to last pair is n minus 1 plus 2, and the last one is n plus 1. And if you look at these pairs, you will see that they all have the same sum, which is n plus 1. And so you just get a sum of n plus 1s. How many? Well, there are n pairs because there is n addends here. So n times n plus 1. And this is n times n plus 1 by this rule. And this is, so dividing by 2, we get exactly this formula. So what did we use here? We used that we can turn the sum around. More generally, if you have a sum like this, you can turn it around. So instead of going from the bottom to the top, you can sum from the top to the bottom. Even more generally, if S and T are two finite sets, and if F from S to T is a bijective map, this means a one-to-one correspondence. It's just a European way to say one-to-one correspondence. Then, if you have a sum over the elements of T, you can relabel it as a sum over all the elements of S. Why? Because these two sums have the same addends. This is why we need F to be a bijection. And this is a particular case of this formula because you can take a bijection from this interval u to v to itself, which just sends the smallest number to the largest, the second smallest to the second largest, and so on. Other particular cases of this rule are these formulas. So this is commonly known as shifting the summation index, and this is known as reflecting the summation index. And you probably have used the analogous formulas for integrals a lot.